Today we're going to take a look at why conditioning on a variable is still a purely observational description and how to make it equivalent to an interventional one. Let's imagine we want to measure if a medical treatment really increases the likelihood of a patient's survival. We know that confounders like the severeness of the condition can affect the outcome and the fact if or at least when the treatment is applied at the same time. Even if we condition on severeness, meaning we only look at one certain degree of it and hold it constant, it still only gives us the direct effect of a specific test group that might be biased based on the severeness of the condition towards a certain outcome. Like for example, if the treatment is only given to patients with a very severe condition in the first place, that group might have different chances of survival in comparison to the rest of the population. It is purely observational information and therefore not enough to prove a treatment's effect. What we want is to measure the effect in a way as if we prescribe the treatment to a patient independent from other influencing factors, like as if we look at the whole population getting the treatment versus not getting it. Obviously, those operations are not always possible or ethical, like forcing someone to smoke to research the effect of lung cancer. But luckily, there are other ways to mathematically reduce an expression from interventional, meaning it contains a do operator, to observational without one, with the help of causal assumptions, even though those two are fundamentally different. This is called identifiability. If we look at our causal graph, the probability distribution for x, y, and t can be factorized by the distribution of x, the one of t depending on x, and the one of y depending on t and x. But how do we transform this to the probability of y enforcing the treatment? Our distribution depending on do t, meaning we set t to 1, will also disconnect any dependencies from t. T will exist no matter what. It's like deleting the node and therefore dependency from x to t and representing that graph as an equation instead. If we use the fact that we can take a multivariate distribution and marginalize parts out of it to separate x from our term here, we're left with the effect of our treatment, assuming an unbiased population is enforced to undergo the treatment. This will give us a causal relationship from purely observational data. Thank you for watching.